Problem 6 is quite similar to the previous problem, as it involves a point rotating around a fixed point or being on a rotating wheel. This problem also considers the angular assumption and its variability over time. The main question it poses is the particle's position at time t equals 0. Well, it's simple, right? If the theta is in radians when the time is in seconds, then at 0 we have 0 and 0. Theta is 2 radians. What is the angular velocity? But we can define anko veljos as the derivative of pos with respect to time, and this goes to the base 402 8t plus 6t squared. So if I evaluate the angular velocity at time t equal to 0, this goes to 0, and then I have that omega is equal to 0. At time t equal to 4, what is omega? So at time t equal to 4, we would have this valued at 4, correct? At time t equals 4, it would be 8 multiplied by 4 plus 6 multiplied by 4 squared. This is, at present, I genuinely have no clue about the precise quantity, but it has been finished at this location, and that amount is 128. 128 radians per second. Omega will be 128 radians per second. Well, now let's consider the acceleration. They request acceleration at time theta 2. Acceleration is the derivative of velocity with respect to time. If this is the expression for velocity, I derive and obtain 8 plus 12t. Therefore, at time t equals 2, the alpha at time t equals 2 would be 8 plus 12 times 2, which would result in 24 and 6, totaling 32, correct? So here we would have alpha equal to 32 radians per second. And the question is whether it is constant or not constant. Simply by looking at the expression of alpha, it has a temporal dependence. So no, gentlemen and ladies, it is not constant. Ready.